Hello, my dear students. I am Dr. Sunira, Assistant Professor, Department of Physics, Government College, Madapalli. Today, we will learn about the index of refraction and dispersion. This is the lecture 3 in the module. First of all, we can check about the information carrying electromagnetic waves. As all of you know, the electromagnetic waves can carry information from the source to the destination. In earlier days, these waves were radiated to space by an antenna. The antenna sent signals everywhere into space. So the signal quality was reduced. In order to rectify this issue, directive antennas were used. But still, the signal quality gets reduced. Then comes transmission lines. Transmission lines are used to guide electromagnetic waves from source to the destination with high quality signals. There are three types of transmission lines. They are the two-wire transmission line, coaxial transmission line, parallel plate transmission line. First, we can check about the two-wire transmission line. This transmission line consists of two parallel wires separated by a constant distance. This gap may be filled with a dielectric. In this figure, you can see a sample of two-wire transmission line. Usually, these cables connect the rooftop antenna to the television. Then comes coaxial transmission line. In this, there are two conducting regions. The first one is an inner conducting wire, which is surrounded by an outer cylindrical cover and separated by a dielectric arranged coaxially. So this is called coaxial transmission line. The following figure shows the coaxial transmission line. You can see there is center core, which is a conducting wire, and there are metallic shield. This represents the second conductor, conducting cylindrical cover. These two are separated by a dielectric insulator. All this setup is inside a plastic jacket. You can see these type of coaxial transmission lines in TV cables. It connects with a set-top box. The third one is parallel plate transmission line. Here, there are two parallel conducting plates. They are separated by a gap which is filled with a dielectric. One example for this is a microstrip. This is used in microwave antenna. Now we can model a transmission line. We can model a transmission line using a series of coupled inductors and capacitors by neglecting the resistance. The diagram is shown below. You can see how many inductors with inductance L and capacitors with capacitance C. The length of the inductor is given by A. The transmission line is driven at the input end, that is Z equal to 0, by a harmonically oscillating charge. The dispersion relation for this system in the dispersive frequency range is given by omega square equal to for C inverse by L sine square Ka by 2. The dispersive frequency range is the pass band which lies from 0 to omega 0, where omega 0 is equal to 2 root of 1 by L. In the low frequency limit, this k approximately equal to 0, or in the continuous limit, the length of the inductor A approximately equal to 0. Then sin Ka by 2 approximately equal to Ka by 2. Substituting these in the expression for phase velocity, we get that v phi square equal to omega square by k square, which is equal to 4 by Lc a square by 4. Now we can derive the expression for phase velocity for transmission line. For that, as an example system, consider a parallel plate transmission line. Let W be the width of the conducting plate along y direction. These plates are separated by a gap G in x direction. The current flows along the z direction. The driving force provides a potential difference capital V between the plates at z equal to 0. And so the current I flows out in the plus z direction onto one plate and returns in the minus z direction on the other. Figure is shown here. Here you can see a sample of parallel plate transmission lines. The x, y, z coordinates are shown in the right side of the figure. From this figure, we can see that the width of the transmission line along the y direction is assumed as W, and along x direction the gap between the plates is represented by G. Here the width of the transmission line W is large compared with the gap G. Similarly, the dimension A, which is shown along the z-axis, is an arbitrary length. We can take it as r small f comparing with the wavelength of the traveling wave. And also we assume that the bottom plate is positive and the top plate is negative, so that the electric field is in the plus x direction. Now we can derive the capacitance per unit length. Assume that Q be the charge displacement on an area of the plate of width W along Y and of length A along Z, as shown in the above figure. Suppose C represents the capacitance of this area of the plate. Then all of you know that the charge on the plate Q is equal to the capacitance into voltage V, C into V. Similarly, the electric field along x direction Ex is equal to Q by WA epsilon 0, or this is equal to CV by WA epsilon 0. The potential is equal to G into Ex, and so the electric field is given by V by G. From the above equation, we get that V by G equal to CV by WA epsilon 0, and this is equal to C by A equal to W epsilon 0 by G. So the capacitance per unit length in the MKS system is given by W epsilon 0 by G. Here W represents the width of the plate along y direction and G represents the separation between the plates. By converting these to Gaussian units, we have to divide the above expression with 4 pi epsilon 0. This gives you C by A equal to W by 4 pi G. Now we will find out inductance per unit length. For that, let us assume the bottom plate is connected with positive terminal of the power supply and the top plate to the negative terminal of the power supply. So, the current flows in the plus Z direction in the bottom plate and minus Z direction in the top plate. Using Biot-Savart law, we get that the magnetic field between the plates is along Y direction. The magnetic field is zero in the region outside the plate. Let L be the self-inductance of the plate. The magnetic flux through the area dA is given by phi equal to B by GA. But dy equal to mu 0 I by W, where I represents the current through the plate. Mu 0 is called the permeability of free space. Now, for varying currents, the self-inductance satisfies the equation L di by dt equal to d phi by dt. For a steady current I, this equation takes the form Li equal to phi. From this equation, we can see that the flux phi equal to Li, which is equal to B by Ga, which is equal to mu 0 I by W Ga. Rearranging the expression, L by A, that is the inductance per unit length, equal to mu 0 G by W. The dispersion relation for a transmission line is given by G phi square equal to omega square by K square equal to 1 by C by A into L by A. We already find out the capacitance per unit length C by A and the inductance per unit length L by A. Substituting these in the equation 8, you get that V phi square, or the phase velocity square, equal to 1 by epsilon 0 mu 0, which is equal to C square. Here C represents the velocity of light in vacuum. So we get that the phase velocity of a traveling wave in a transmission line is equal to the velocity of electromagnetic wave in vacuum, that is C. Actually, this is a general result. The phase velocity for any transmission line consisting of two isolated identical straight parallel conductors in vacuum is C. Now we can derive the expression for phase velocity in the presence of a dielectric. For that, assume that the gap between the plates of the transmission line is filled with a dielectric having the dielectric permittivity epsilon and the magnetic permeability mu. we can define the relative dielectric permittivity such that it is the ratio of dielectric permittivity of the medium to the dielectric permittivity of the vacuum. So, the relative dielectric permittivity epsilon R is equal to epsilon by epsilon 0. Similarly, we can define the relative magnetic permeability mu R such that mu R equal to mu by mu 0. Now, the capacitance becomes epsilon R C and the inductance is modified to mu R L. Now, replacing the capacitance C and the inductance L in the above equation with the modified capacitance and inductance, we get the phase velocity of the system V phi equal to V phi vacuum divided by root of mu R epsilon R. This is equal to C by root of mu R epsilon R. The voltage across the plate produces the electric field and the current along the plate generates the magnetic field between the plates. The electric and magnetic field must travel with the same velocity as the current and the voltage waves. When the space is vacuum, the velocity is c for traveling waves of transmission lines. But it is so that c is the velocity of all electromagnetic waves in vacuum. This is the velocity of all electromagnetic waves in such a material, whatever their source, that is, whether they're coming from a radio antenna or from a distant star or from a distant light pulse. Now we can learn about the dispersion relation. The dispersion relation depends only on the inherent properties of the waves and the medium. The electromagnetic waves can be produced by applying voltage at the end of the transmission line or by means of a transmitter or antenna. These represent the different boundary conditions of the system. The dispersion relation is independent of the boundary condition. The term root of mu r epsilon r is called the index of refraction. It is designated by n. There are many forms for the refractive index or the index of refraction. They are n equal to root of mu r epsilon r, and that's equal to root of mu epsilon by mu 0 epsilon 0, which is equal to c by v phi. So, the index of refraction or the refractive index is the ratio of velocity of light in vacuum to the velocity of light in the medium. The wavelength lambda modified as 1 by n into c by f, that is lambda in vacuum divided by n. Similarly, the wave number k is changed to n k vacuum, where k vacuum is the ratio of omega by c. So, the index of refraction for common material for yellow sodium light of lambda 5893 angstrom are given by AR 1.0002906, water 1.33, zinc ground glass 1.52. Now what is dispersion? A prism or wedge-shaped transparent material bends an incident light by an amount depending on its color. It is called dispersion. The wavelength is different for different colors. So each color in a parallel beam of white light are bent through different angles and they are dispersed. They emerge with different colors and give a rainbow-like colored pattern. The following figure shows the dispersion of visible light by a prism. Here you can see a beam of white light is incident on the prism on the side PQ, and they refracted through the prism at the point B and emerging out through the side PR. In that side there is a screen, and that screen you can see the colored spots. White light split into 7 colors. From the above diagram, you can see that the blue light is bent more than red. The wavelength of blue is less than that of the red. The deviation is greater for lesser wavelength. Red has large wavelength, so its deviation is less. Now, what is refraction? A beam of light of a given color is bent or refracted whenever it encounters a surface where the phase velocity takes on a new value or the phase velocity changes. That means the refractive index change at the surface. The amount of refraction depends on the ratio of the refractive index of the incident medium to that of the refracting medium. To prove this condition, we can first check what is angle of incidence and angle of refraction. The amount of refraction depends on the angle of incidence. It is the angle that the incident light beam makes with the normal to the surface. The angle of refraction is defined as the angle the refracted beam makes with the normal to the surface. The angle of incidence and the angle of refraction to be positive angles between 0 degree to 90 degree. Now you can see the figure. In this figure, the light ray passing through one medium 1 and enter to the second medium 2. Here the normal is shown as a dashed line, black colored dashed line. Incident ray makes which is shown here as red in substance 1, which makes an angle with the normal to the surface. This is called angle of incidence. Similarly, when this incident ray enters to the substance 2, it changes its angle by a little, and the ray is called refracted ray. This ray now makes an angle with the normal to the surface, which is called angle of refraction. Consider A wavefront. Wavefront means the locus of points with the same phase in a wave. The wavefronts are perpendicular to the direction of propagation of light. In the following figure, you can see incident wavefront and refracted wavefront separated by a boundary. In this figure, the black lines, arrowed lines represent incident rays and refracted rays. In red straight lines represent incident wavefront and blue straight lines represent refracted wavefront. When a wavefront reaches the boundary, one end of it reaches there before the other end. In the above figure, the wavefront AB reaches at the boundary. Then the point A reaches at first. So the phase velocity decreases at one end of the wavefront before the other end. The angle of the wavefront changes at the boundary due to the change in phase velocity. It is shown in the above figure where the incident wavefront AB changes to the refracted wavefront CD. Consider the two right triangles in the figure with a common hypotenuse AC. From the figure, BC equal to AC sin I, AD equal to AC sin R. Let C be the time taken by the wave to travel BC distance in medium 1. At the same time, the wavefront travels a distance AD in medium 2. That is, BC equal to L1 equal to CT by N1, AD equal to L2 equal to CT by N2. Therefore, CE equal to N1 L1 equal to N2 L2. Inserting these equations in equation 11, CT equal to N1 AC sin I, that is equal to N2 AC sin R. Cancelling common terms AC in both sides, N1 sin I equal to N2 sin R. Equation 13 is called Snell's law of refraction. The dispersion of the prism results from the fact that the index of refraction is greater for blue than for red light. In this lecture, we learned about the transmission lines and their modeling. And then we derived the expression for phase velocity for transmission lines. Then we learned about the index of refraction. After that, we studied about the dispersion of light. Finally, we learned about the refraction and derived the Snell's law. This lecture is prepared based on Waves by CRAWFORD Jr. In that text, chapter 4 gives your waves. In that section 4 to examples 4 and 5 are used to explain transmission lines and its phase velocity. So you have to read that section. After that, the index of refraction and the dispersion. These are described in section 4.3. After reading all these and hearing this lecture, you can try to answer the following questions. If you get the answer properly, you can make sure that you learned everything about this section. Then you can do as many problems as you can using your textbooks. These are different questions in this section. In the section we have already learned the main question. And after finding out all the answers for these questions, you can make sure that you learn well all these sections. Finally, I have to take one more section to finish this part. That should be done in another lecture. Thank you.